we're going to look at the original cyclotron from Lawrence. The copper Ds that made up the cyclotron were about a ½ meter in radius. The largest magnetic field strength that they could reasonably make at the time was about 1/10 of a Tesla. And if that cyclotron is accelerating a beam of protons, we're going to find what their maximum speed is going to be. The protons are getting accelerated by a voltage difference when they would pass from one D to another, and the phase of the voltages would change so that it was always accelerating the beam. But while they were inside the D, the protons were moving on a circular path. So they were in uniform circular motion while they were in the D. And then the beam is what would emerge from just a hole. So for the part where they're in uniform circular motion, we know that the magnetic force is going to provide the radial force for circular motion. And the magnitude of that magnetic force is going to be the magnitude of the charge times the speed times the magnetic field strength times sine of 90 degrees, because V is perpendicular to B by the design of the cyclotron. So sine of 90 degrees, so just replace that with 1. There's a V on each side of the equation. So we can cancel that out. So the maximum speed is going to be where the radius is maximum. So out at the outer edge. So we'll have Q times the magnetic field strength times the radius over the mass of a proton. Putting in numbers for that. B max. So the charge of a proton is the elementary charge, 1.602 times 10 to the minus 19 coulombs. Magnetic field strength, 1/10 of a Tesla, so as a Newton per meter per amp. Maximum radius, 0.5 meters. And then we need to divide by the mass of a proton, 1.67 times 10 to the minus 27 kilograms. All right. So carry out that arithmetic. We're going to get V max 4.80 times 10 to the 6th. Now the units are sort of ugly, so we'll look at that just sort of on its own. I'll have a coulomb. I will have a Newton, which is a kilogram meter per second squared. I have another meter in the numerator. In the denominator, I'll have that kilogram, and I'll have 1 over a meter for that, and then 1 over an amp would be a second per coulomb, since amp is in the denominator. So a lot of things cancel out. Get a coulomb to cancel out with a coulomb. Get a kilogram to cancel with a kilogram. 1 power of second with 1 power of second. And 1 power of meter. 1 power of meter. So the unit started off looking pretty ugly, but it does all work out, which is a good way to check your answer. Because if this right hand side did not turn out to be meters per second, then no, I'd have to have some mistake in setting up this equation and putting values in. And for Lorenz's original cyclotron, you can tell from his answer that you're getting protons a bit faster than like 1% the speed of light. So therapeutic cyclotrons used today for like proton beam therapy for cancer treatment, or cyclotrons that are used to make isotopes that are used in medical imaging. Those sorts of cyclotrons are going to be, not quite desktop, like a half meter is a pretty good radius, but not too far from a desktop sort of device. Easily fit within a shielded room.